All right, here we go. Last thing that we need to talk about um, for some of y'all is the turning points. Okay, now there is a rule when it comes to the turning points. The rule is the number of turning points is one less than your highest power. If you want to pause the video and read this paragraph to yourself and try to decipher it, please feel free to do so. But the easiest way that I have found to teach this and make the rule is to know that the number of turning points, the maximum number of turning points, I should say, is one less than your highest power. So, for example, here, we know that this is a linear equation. And with a linear equation, we would have something like y equals mx plus b, with our power being 1. So, for the rule of turning points, it's 1 less than your highest power. Well, what's 1 minus 1? That's 0. What do we know about a line? It has no turning points. That makes sense. With a quadratic, if we have y equals x squared, okay, my highest degree is 2, but 1 less than your highest degree is 1. And then how many turning points do we have here? Just 1, and that's called the vertex. We've dissected that. Now, cubics play a different game. Cubics are a little weird, and that's why I emphasized earlier that it's the maximum number of turning points. Because with a cubic, you know you have x cubed, so your number of turning points would be at most 2. 1, 2. However, sometimes with cubics, they do not have a distinction between the concavity. What do I mean by the concavity? Between this actual turning point and this actual turning point, you'll notice here that there's no direct shift in the turning points. So that's an example of sometimes where it would be 0. So if you're trying to determine how many actual turning points there are, you're gonna need a calculator when you start dealing with cubics. So on this next slide, go ahead and get your calculator out, because that's how we are going to do these next few. So it says, what is the graph of each cubic function? And then describe the graph. So we're going to describe the number of turning points. So get your calculator out. Let's go to y equals. And I'll get mine out. I'll pull mine up here too. And in y equals, type in 1/2 x cubed. Now when you type in that 1/2, you can do that a couple of different ways. Let me clear out what I got in here. If you want to type it in as a fraction, you can. I'm more comfortable with just saying 0.5. And then x, and then there's no button for cube, so we just have to do the caret and then 3. And then we can hit graph. Now you'll notice here, okay, this looks real similar to that one that we just looked at on the last slide. There is no definite change in the direction between the turning points. So here we would say that there would be 0 turning points for part A. I know you want to say it's a maximum of 2, which it is, but when you graph it, there's actually 0 turning points. And same thing with B. We're going to graph it. So go back to y equals, and we're going to type in 3x minus x cubed. This is clearly not in standard form, but our calculator should still graph it for us. And we can clearly see here that there are 2 turning points. Perfect. And you're going to do the same thing on A and B. And I will go ahead and tell you A has 2 turning points, and then B should have no turning points. Perfect. Okay. If you want to do the do you know how, that would be super awesome. If you still have questions, we would be more than happy to answer them during class or office hours or when we are able to talk with you next. If you are an Honors Algebra 2 student, don't end the video just yet. We have one more thing to go over with you all. But every other person, you can just go ahead and stop your video and work on your homework. All right. Honors friends, here we go. How do we find the power? Okay. It says here, suppose you're given a set of polynomial function outputs. You know that their inputs are an ordered set of x values in which consecutive x values differ by a constant. Okay, so by analyzing the difference of consecutive y values, it's possible to determine the least degree polynomial function that could generate the data. Okay, so what this is saying is that I'm going to give you a table of values, and based off of those table of values, I want you to tell me, is that a table of values for a linear? Is that a table of values for a quadratic, a cubic, a quartic? What is it? Okay. Now, in order to determine that, you have to figure out the difference in the y values. Okay. So if the difference is constant after the first time, it's going to be a linear. If the second difference, but not the first, are constant, then it's a quadratic. And if the third differences are constant, then it's a cubic, and so on. I think this will make a little bit more sense when I do an actual problem. So let's look at problem number 4 here. On problem number 4, it says, what is the degree of the polynomial function that generates the data shown at the right? So we're looking at this table of values here, and we notice that our x values are consecutive, right? Like these are all consecutive. So what I need to do is I need to take my y values and find the difference in those y values until that difference is constant. So for example here we go. I'm going to dissect this whole problem and then we're going to do another one. If you have -1, -7, -3, 5, 11, and 9, -7, okay? The difference between 1 and -7 is -6. From 1 to -7, you went down 6. From -7 to -3, you went up 4, and then so on. From -3 to 5, you went up 8. From 5 to 11, you went up 6. From 11 to 9, you went down 2, and then from 9 to -7, you went down 16. This first difference is not the same number. So this is not linear. Not linear. Well, let's keep going until we get a difference that is consistent. So from -6 to 4, you went up 10. From 4 to 8, you went up 4. From 8 to 6, you went down 2. 6 to -2, you went down 8. From -2 to -16, you went down -14. So the second difference would be a quadratic. It's not constant, so it's not a quadratic. Let's keep going. From 10 to 4, you went down 6. From 4 to -2, you went down 6. Hey, -2 to -8, you went down 6. -8 to -14, you went down 6. So the third difference was where I saw that constant. So this is in fact a representation of a cubic polynomial. Is this tedious? Yes. Difficult? No. Okay. Now, I want you to pause the video and see if you can do this last question on your own. If you need some help, just play the video at any time, catch up to where I'm at. And I got some pretty large numbers here, so this might take us a little bit. So I have 23, -16, -15, -10, -13, -12, and then 29. Okay, here we go. We're going to find the difference between the first two. From 23 to -16. What did you go down? Well, you went down 23, and then you went down another 16. That gives you -39. From -16 to -15, you went up 1. From -15 to -10, you went up 5. From -10 to -13, you went down 3. From -13 to -12, you went up 1. And then from -12 to 29, you went a total of 41. So is this linear? Nope, because it wasn't constant. From negative 39 to positive 1, you went up 40. From 1 to 5, you went up 4. From 5 to negative 3, you went down 8. From negative 3 to 1, you went up 4. Gosh, it's early. From 1 to 41, you went up 40. Yep. Okay, here we go. Not a quadratic. Sad. Let's see if we can make this next one work. From 40 to 4, you went down 36. From 4 to negative 8, you went down 12. From negative 8 to 4, you went up 12. From 4 to 40, you went up 36. Still not there. Let's keep going. From negative 36 to negative 12, you went up 24. From negative 12 to 12, you went up 24. From 12 to 36, hey, you went up 24. So let's look at how many differences we had to do. It's not linear. It's not a quadratic. It's not a cubic. It is a quartic. And we are done. If you have any other questions, please feel free to reach out to us. We would love to help you any way that we can.